Hi and welcome. At this video, you will see how to use the energy conservation equation, which means that the potential energy and the kinetic energy before and after scenario on a car that is being released from a starting position, which is at zero velocity, so it's at rest, and then you will let go of it and it will move to the end, but this time it's not totally at the very end or end of the ramp where height is zero. It is given a certain height of, in our measurement, it's 0.02. Okay, let me just wait for the camera to reset. 0.02, while the original height is 0.19 meters. A mass of m is provided, and using this equation, again, the conservation of energy or mechanical energy conservation, where the total energy, which is potential gravitational potential energy plus the kinetic energy in the beginning, is equivalent to the um, gravitational potential energy at the endpoint plus the kinetic energy at the endpoint, and you are supposed to solve for the velocity. So why don't we apply this concept and see what is the velocity of the car when it reaches that point. So let's just plug in the values. We don't know the mass, so let's put mass m. G is the acceleration due to gravity, where G is assumed to be 10 meters per second squared. So let's put 10. Plug in the value of the higher h, which is the starting h. So instead of h sub 1, we're using h to represent the higher h. And that is 0.19 plus 1/2 the mass and the velocity, initial velocity of 0 squared. However, we know right away that any number multiplied by 0 involving operation of multiplication or division is immediately 0. The mass at the end is still the same mass. Potential gravitational energy is simply mass times g times height, where g is 10 meters per second squared. The new height at the end is 0.02 plus 1/2 mv squared. So my suggestion is to simplify numericals first. So 10 times 0.9, this will change into m multiplied by 1.9 plus 0 equivalent to 10 times 0.02. So that's m 0.2. So you multiply it by 10. So let's put 0.2 plus 1/2 mv squared. So now that we have simplified the numerical values, our next step is to look if I can move this m to the other side of the equation, or is there a possibility that we can leave velocity by itself in one side of the equation. Some of you might say, well, it's simple. All we have to do is subtract both sides by m 0.02. So this will be cancelled. Now it's 0. And I will multiply m or not 0.02, but 0.2. Sorry, 0.2. So minus 0.2. Now we can subtract this, which is 1 point, so 9 minus 2 is 0.7. Now we can rewrite our equation. Now we have m times 1.7. We can just ignore 0. We can ignore this 0. Now I have 1/2 mv squared. So I want my v to be by itself in one side of the equation. The wisest thing to do is to of course, get rid of 2 first and then get rid of m. Now, in order to get rid of 2 on one side of the equation, since 2 is in the denominator, so all we have to do is multiply it by 2. So let's multiply this by 2. Okay. So let's multiply both sides by 2. You notice since it's in the denominator right here and now it's in the numerator, so it cancels out my 2. Now m is also in the numerator, so I have to multiply it by a number which is the inverse, or I will multiply it by the denominator of m, so 2 over m or 2 over m, which lasers cancels out my m here, and it also cancels out my m right here. So now what's left is 2 multiplied by 1.7, and that is equivalent to v squared. So 2 times 1.7 is 3.4 equals v squared. However, I don't want my v squared value, but I want my square. I want my v value. So next thing for us to do is to take the square root of both sides of the equation in order to get rid of the square from your velocity, giving you a 3.4 square root. So let me just use the calculator. 3.4, that is 1.8. That is equivalent to v. Or we can say that v is simply 1.84 meters per second. So this will be your velocity in case you are required to solve for the velocity. Okay, so the velocity, what is the ideal velocity if you let go of the car and it will travel at this height? Hope it will help you in answering some of those tricky questions that you might encounter.